Imagine a world where everything you know, everything you see, everything you touch is only 5% of the story. A world where the vast majority of reality is a silent, invisible presence that passes through you, through the earth, and through the stars, every single second, without leaving a trace. This is not a thought experiment. This is the universe we inhabit. We are surrounded by a cosmic shadow, a hidden architecture of particles and forces that dictate the fate of galaxies, yet remain utterly elusive to our senses. This is the mystery of the invisible space particles, and today we are going to hunt them down. We are going to journey into the heart of the unseen, from the tiniest, most ephemeral subatomic ghost to the colossal, dark energy that is tearing the cosmos apart. We will explore the particles that allow the sun to shine, the waves that ripple the fabric of space-time, and the cosmic remnants so dense they create the hardest material in the universe. We will confront the ultimate questions of existence. What is reality made of? And why is so much of it hidden? If this journey into the profound and the invisible resonates with the deep, quiet wonder inside you, if you feel the pull of the cosmic mystery, then join our crew. Hit that like button, subscribe to Cosmo Depth, and ensure you never miss another flight into the unknown. Your support is the fuel that powers this channel, allowing us to continue mapping the most distant and the most hidden corners of the universe. Now, let the hunt begin. Our first target is the most numerous, yet most subtle, particle in the cosmos, the neutrino. To understand the neutrino, we must first go back to the 1930s, to the problem of beta decay. Scientists observed that when a neutron decayed into a proton and an electron, the energy of the resulting particles did not add up. It was as if energy was simply vanishing, a direct violation of the fundamental law of conservation of energy. Niels Bohr, one of the titans of quantum mechanics, was so desperate that he suggested the law of conservation of energy might simply not hold true at the subatomic level. It was a radical, almost heretical idea. The idea that a fundamental law of physics could be violated was a terrifying prospect for the scientific community, a crack in the foundation of their ordered universe. The stakes were incredibly high, and the solution had to be equally radical. The conservation of energy was the bedrock of classical physics, and its potential failure sent shockwaves through the intellectual world. Enter Wolfgang Pauli, a brilliant but notoriously sharp-tongued physicist. In 1930, Pauli wrote a desperate apologetic letter to a group of physicists attending a conference in Tübingen, Germany. He couldn't attend because he was going to a dance, but he proposed a desperate remedy to save the law of conservation of energy. He suggested that an unseen, electrically neutral particle with a mass no greater than 1% of a proton was carrying away the missing energy. He called it the neutron, but Enrico Fermi later renamed it the neutrino, the little neutral one, to distinguish it from the much heavier neutron found in the nucleus. Pauli's proposal was a masterpiece of theoretical physics, a particle invented purely to preserve a symmetry in nature. He was so convinced of its elusiveness that he famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." For over 2 decades, the neutrino remained a purely theoretical construct, a mathematical necessity to balance the books of physics. The neutrino was born out of a crisis of faith in the fundamental laws of the universe, a silent guardian of the principle of conservation. The sheer elusiveness of the neutrino is its defining characteristic. It interacts only through the weak nuclear force and gravity. The weak force, as its name suggests, is incredibly short-ranged and weak. This means that a neutrino can pass through a light year of solid lead with only a 50% chance of interacting with a single atom. Think about that. A light year of lead. To put it another way, the mean free path of a typical solar neutrino in water is about 10 to the power of 18 meters, or roughly 100 light years. This near total detachment from ordinary matter is what makes them the ultimate ghost particles. Yet it is also what makes them invaluable as cosmic messengers. They are the only particles that can escape the most dense and violent environments in the universe, carrying pristine information about their origin. Right now, as you listen to this, hundreds of trillions of neutrinos are streaming through your body, through the walls of your home, through the entire planet, and they are doing so without any interference whatsoever. The vast majority of them originate from the nuclear fusion reactions deep within the core of our Sun. Every second, the Sun converts 600 million tons of hydrogen into helium, and in the process, it unleashes a torrent of these ghost particles. The flux of solar neutrinos hitting the Earth is staggering. About 65 billion neutrinos pass through every square centimeter of your body every second. They are the ultimate cosmic messengers, carrying information directly from the heart of the Sun, a place no photon can escape for thousands of years. While a photon born in the Sun's core takes hundreds of thousands of years to diffuse to the surface, undergoing countless scatterings, a neutrino takes a mere 8 minutes to travel from the core to your eye. They are a real-time snapshot of the Sun's engine room, a direct line of communication to the star's nuclear furnace. The first successful detection of the neutrino came in 1956 by Clyde Cowan and Frederick Rines in an experiment near a nuclear reactor. The reactor was a powerful source of antineutrinos, and the experiment, known as Project Poltergeist, confirmed Pauli's desperate remedy. The ghost was real. They used a target of water mixed with cadmium chloride, where the antineutrinos would interact with protons to produce a neutron and a positron. The subsequent detection of the characteristic gamma rays from the annihilation of the positron and the capture of the neutron by the cadmium provided the definitive proof. It was a monumental achievement, a triumph of experimental ingenuity over the particle's inherent elusiveness, and it earned Rines the Nobel Prize 4 decades later. But the real mystery began when scientists tried to count the neutrinos coming from the Sun. This led to the famous solar neutrino problem. In the late 1960s, Ray Davis Jr. built a massive detector deep inside the Homestake gold mine in South Dakota. It consisted of a tank filled with 615 tons of perchlorethylene, a common dry cleaning fluid. The idea was simple. A neutrino of the right energy could interact with a chlorine atom, turning it into a radioactive argon atom. Davis would then count the argon atoms. The results were shocking. Davis was only detecting about 1/3 of the neutrinos predicted by the standard solar model, the highly successful theory that describes how the Sun works. For decades, this discrepancy was a crisis in physics. Was the standard solar model wrong? Was our understanding of nuclear fusion flawed? Or was our understanding of the neutrino itself incomplete? The answer, as is often the case in cosmology, was the most mind-bending option. The neutrino was changing its identity mid-flight. The standard model of particle physics states that there are three types, or flavors, of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. The Sun only produces electron neutrinos. Davis's detector was only sensitive to electron neutrinos. The solution, proposed by Bruno Pontecorvo, was neutrino oscillation. Neutrino oscillation is a purely quantum mechanical phenomenon. It means that as a neutrino travels, it oscillates, or changes, between its three flavors. The electron neutrinos produced in the Sun were oscillating into muon and tau neutrinos on their 8-minute journey to Earth. Since Davis's detector could only see the electron flavor, it was missing the other 2/3. The ghost particle was not just elusive, it was a shapeshifter. This was definitively confirmed by the Sudbury Neutrino Observatory, SNO, in Canada, which was able to measure all three flavors of neutrinos, proving that the total flux matched the solar model's prediction. But the electron neutrino flux was indeed only 1/3 of the total. The SNO experiment was a masterpiece of scientific design, using heavy water to distinguish between the different neutrino flavors, finally resolving the decades-long solar neutrino problem and confirming the revolutionary concept of neutrino oscillation. This discovery had a profound implication. For a particle to oscillate, it must have mass. The standard model had always assumed neutrinos were massless, like photons. The discovery of neutrino oscillation proved that the standard model was incomplete, and that neutrinos, though incredibly light, do possess mass. This mass, though tiny, is a crucial piece of the cosmic puzzle, and it is a key to understanding the total mass of the universe. The total mass of all the neutrinos in the universe, though individually tiny, is collectively enormous, second only to the mass of the stars. The ghost particle, it turns out, is a cosmic heavyweight. The philosophical implication of neutrino oscillation is staggering. It means that the identity of a particle is not a fixed, immutable property, but a fluid, evolving state. A neutrino is not simply an electron neutrino. It is a superposition of all three flavors simultaneously, only collapsing into a single identity when measured. This is quantum mechanics on a cosmic scale, a reminder that the fundamental building blocks of reality are far stranger than our classical intuition allows. The search for the absolute mass of the neutrino, a value that remains one of the most sought-after numbers in physics, is the next great frontier. Experiments like Katrin are attempting to measure this mass by precisely observing the energy spectrum of electrons emitted during beta decay, pushing the limits of experimental precision to confirm the tiny but crucial mass of the ghost particle. The mass of the neutrino is not just a number, it is a constraint on the standard model, a window into physics beyond our current understanding, and a key to understanding the early, hot universe where these particles were once a dominant component of the energy density. The fact that neutrinos have mass is the first crack in the standard model, the first definitive proof that there is physics beyond the established rules, a tantalizing hint that the universe is far more complex than the most successful theory in history suggests. This tiny mass is the key to unlocking the secrets of the early universe, the formation of the elements, and the ultimate fate of matter. The discovery of neutrino mass necessitates the existence of a mechanism outside the standard model to generate it, potentially involving a hypothetical particle called the sterile neutrino, which would not interact via the weak force at all, making it an even more profound ghost particle. The neutrino, the particle invented to save a law of physics, ended up breaking the most successful theory of particle physics, a beautiful irony that underscores the relentless progress of science. The discovery of neutrino oscillation and the realization that these particles carry mass transformed the hunt for the invisible. The challenge shifted from simply proving their existence to using them as a new lens through which to view the universe. This gave rise to the era of neutrino astronomy, a new branch of science dedicated to catching these cosmic messengers. To catch a particle that can pass through a light year of lead, you need a detector that is absolutely massive and incredibly pure. You need to maximize the target volume and minimize the background noise. This is why neutrino observatories are not built on mountaintops. They are built deep underground, underwater, or even in the Antarctic ice. The Earth itself becomes the shield, filtering out the constant barrage of cosmic rays and other background radiation, leaving only the elusive neutrinos to interact. One of the most spectacular examples of this extreme engineering is the IceCube Neutrino Observatory. Imagine a cubic kilometer of the purest, deepest ice at the South Pole. Now, imagine drilling 86 holes, each 2,450 meters deep, and lowering over 5,000 light sensors, called digital optical modules, DOMs, into the ice. This is IceCube, a telescope with no lens, no mirror, and no moving parts, using the Antarctic ice as its detection medium. The construction of IceCube was an engineering feat of epic proportions, drilling through 2.5 kilometers of solid ice in one of the most hostile environments on Earth. The result is a detector the size of a small city, a true monument to the human desire to see the unseen. IceCube is designed to catch the highest energy neutrinos, those born in the most violent, cataclysmic events in the cosmos. When a high-energy neutrino finally interacts with an atom in the ice, it produces a charged particle that travels faster than the speed of light in the ice. This creates a cone of blue light, known as Cherenkov radiation, the optical equivalent of a sonic boom. The DOMs detect this faint blue light, and by timing which sensors light up first, scientists can reconstruct the neutrino's path, tracing it back to its cosmic source. The ability to reconstruct the path of a neutrino with such precision allows scientists to pinpoint the source of these high-energy particles, opening up a new era of astrophysics. The precision of the timing is measured in nanoseconds, a level of accuracy required to map the trajectory of a particle that has traveled billions of light years. IceCube's greatest triumph came in 2017 when it detected a high-energy neutrino and traced its origin back to a blazar, a supermassive black hole at the center of a galaxy, firing a jet of particles directly at Earth, 4 billion light-years away. This was a landmark moment for multi-messenger astronomy, the practice of observing the universe using different messengers: light, photons, gravitational waves, and now neutrinos. The neutrino confirmed the blazar as a source of high-energy cosmic rays, solving a decades-old mystery about where these particles originate. The ability to correlate a neutrino detection with a flare of light from a distant object provides an unprecedented level of certainty about the source of the most energetic particles in the universe. This single event demonstrated the power of using multiple cosmic signals to study the universe, a technique that is rapidly becoming the standard for modern astrophysics, allowing us to cross-reference the universe's whispers with its visible screams. Across the globe, in the deep waters of the Mediterranean Sea, another colossal detector is taking shape. KEM 3NET cubic kilometer neutrino telescope. KM3NET is a network of deep-sea detectors anchored to the seabed and extending hundreds of meters into the water column. Like IceCube, it uses the surrounding medium, in this case seawater, to detect the Cherenkov light produced by neutrino interactions. The advantage of KM3NET is its location in the Northern Hemisphere, allowing it to observe parts of the sky that IceCube cannot, particularly the galactic center, a region dense with potential neutrino sources. The KM3NET array is designed to be a more versatile instrument, capable of detecting neutrinos across a wider range of energies, including those that pass through the Earth before interacting in the water. The Earth acts as a giant filter, allowing only the most penetrating neutrinos to pass through, a technique that helps scientists distinguish between cosmic neutrinos and those produced in the Earth's atmosphere. The deep-sea location provides a naturally dark and quiet environment, shielded from cosmic rays by the water column, making it an ideal location for the sensitive detection of these elusive particles. The KM3NET detector is a network of vertical strings, each anchored to the seabed and supporting a series of optical modules, a delicate, high-tech fishing net cast into the abyss to catch the most elusive cosmic prey. We now leave the realm of the subatomic ghost and turn our attention to a phenomenon that is equally invisible, yet infinitely more profound: gravitational waves. These are not particles, they are ripples in the very fabric of space-time, the four-dimensional stage upon which the cosmic drama unfolds. The concept of gravitational waves is a direct consequence of Albert Einstein's general theory of relativity, published in 1915. Einstein revolutionized our understanding of gravity, not as a force, but as a curvature of space-time caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, and any marble rolled nearby will curve toward the ball. The bowling ball is a star or a planet, and the rubber sheet is space-time. The elegance of this geometric interpretation of gravity is one of the greatest intellectual achievements in human history, replacing Newton's mysterious action at a distance with a tangible, if invisible, deformation of reality itself. If gravity is a curvature, then any change in that curvature must propagate outward, just as a pebble dropped into a pond creates ripples. Einstein predicted that when massive objects accelerate violently, such as two black holes spiraling into each other, they should create these ripples, traveling outward at the speed of light. These are gravitational waves. The energy carried by these waves is immense, but the effect on the fabric of space-time is so subtle that Einstein himself doubted they would ever be detected. He famously spent years struggling with the mathematical complexities of his own theory, at one point even mistakenly concluding that gravitational waves did not exist, a testament to the profound difficulty of grasping the implications of general relativity. For decades, gravitational waves were a purely theoretical construct, a beautiful mathematical prediction that seemed impossible to verify. The reason for this is their incredible subtlety. By the time a gravitational wave reaches Earth, the ripple is so faint that it stretches and compresses space by a factor of less than 1 part in 10 to the power of 21. To put that into perspective, detecting a gravitational wave is equivalent to measuring a change in the distance between the Earth and the nearest star, Proxima Centauri, by the width of a human hair. The challenge was to build a detector sensitive enough to measure a change in distance smaller than the nucleus of an atom. This led to the creation of the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO is a marvel of precision engineering, consisting of 2 identical detectors, one in Hanford, Washington, and the other in Livingston, Louisiana, separated by over 3,000 kilometers. Each detector is an L-shaped vacuum chamber with arms 4 kilometers long. A laser beam is split and sent down each arm, reflected by mirrors at the ends, and then recombined at the starting point. In the absence of a gravitational wave, the 2 beams should cancel each other out perfectly. The entire apparatus is housed in a near-perfect vacuum, and the mirrors are suspended by delicate fused silica fibers to isolate them from all terrestrial vibrations. A testament to the extreme measures required to listen for the faintest whispers of the cosmos. The mirrors themselves are the most perfect ever created, polished to an accuracy of a few atoms, a necessary requirement for the interferometer to function at the required sensitivity. When a gravitational wave passes through, it momentarily stretches space in one arm and compresses it in the other. This tiny differential change in distance means the laser beams no longer cancel perfectly, creating a measurable flash of light. By using 2 detectors thousands of miles apart, scientists can confirm that the signal is a genuine cosmic event and not local noise, such as a passing truck or an earthquake. The time delay between the arrival of the signal at the 2 detectors allows scientists to triangulate the source of the wave in the sky. The ultimate triumph came on September 14, 2015. LIGO detected a signal that lasted for only a fraction of a second, a distinct chirp that rapidly increased in frequency and amplitude. This signal, designated GW150914, was the sound of 2 black holes, one 36 times the mass of the Sun and the other 29 times, spiraling into each other and merging to form a single 62 solar mass black hole. The missing 3 solar masses were instantly converted into pure energy in the form of gravitational waves, a burst of power that briefly outshone all the stars in the observable universe combined. It was the first direct detection of gravitational waves, a century after Einstein predicted them, and it opened a brand new window onto the cosmos. The observation confirmed not only the existence of gravitational waves, but also the existence of binary black hole systems, objects that were previously only theoretical, and provided the first direct test of general relativity in the regime of strong gravity. Since that first detection, LIGO, along with its partners Virgo in Italy and Kagra in Japan, has detected hundreds of events, primarily the mergers of black holes and neutron stars. Each detection is a direct observation of the most violent events in the universe, providing insights into the extreme physics of gravity that are impossible to obtain with light. The analysis of this chirp signal allows scientists to determine the masses, spins, and distances of the merging objects with incredible precision, providing a unique probe of stellar evolution and the distribution of black holes in the universe. The gravitational wave spectrum is a rich tapestry of cosmic events, each chirp a unique signature of a cataclysmic merger. But the current generation of detectors is only sensitive to high-frequency gravitational waves, those produced by stellar mass objects. To detect the low-frequency waves produced by the mergers of supermassive black holes, the giants at the centers of galaxies, we need a detector the size of a galaxy. This is where the Pulsar Timing Array, PTA, comes in. APTA treats a network of millisecond pulsars, rapidly rotating neutron stars that emit incredibly precise beams of radio waves, as a colossal gravitational wave detector. Pulsars are the most accurate clocks in the universe. As a low-frequency gravitational wave passes between Earth and a pulsar, it subtly stretches and compresses the space-time, causing the arrival time of the pulsar's radio pulses to be slightly delayed or advanced. By monitoring dozens of these pulsars across the galaxy, scientists can look for a specific correlated pattern of timing deviations, the Hellings and Downs curve, that is the unique signature of a gravitational wave background. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, announced the detection of a persistent, low-frequency gravitational wave background. This background is believed to be the collective roar of thousands of pairs of supermassive black holes, each pair spiraling toward a merger in the centers of distant galaxies. The universe is not silent. It is humming with the low-frequency rumble of merging cosmic giants. The PTA has opened the door to the nanohertz gravitational wave window, allowing us to listen to the symphony of the universe's largest structures. Gravitational waves are the ultimate invisible force, a direct manifestation of the geometry of space-time. They are the universe's way of whispering its most violent secrets, and our ability to listen is a testament to the ingenuity of the human mind. The future of gravitational wave astronomy is even more ambitious. The Laser Interferometer Space Antenna, LISA, a planned space-based observatory, will consist of 3 spacecraft forming a giant triangle with arms millions of kilometers long. LISA will be sensitive to an entirely different range of frequencies, allowing it to detect the mergers of intermediate mass black holes and the gravitational waves produced by the very early universe, potentially providing a direct probe of the physics of the Big Bang itself. The ability to observe the universe across the entire gravitational wave spectrum, from the high-frequency chirps of stellar mass mergers to the low-frequency hum of supermassive black holes, is transforming our understanding of cosmic evolution, revealing a universe that is far more dynamic and violent than we ever imagined. The invisible ripples are the soundtrack to the cosmos, and we are finally learning to hear the music. The philosophical implication of gravitational waves is that space and time are not the static, unchanging backdrop that Newton envisioned. They are dynamic, elastic entities that can be stretched, compressed, and warped by the presence of mass and energy. The detection of these waves is a direct confirmation that we live in a 4-dimensional universe where the geometry of reality is constantly in flux. A profound shift in our understanding of the fundamental nature of existence. The gravitational wave background detected by the PTA is a relic of the universe's history, a fossil of the most massive mergers that have occurred over cosmic time, a cosmic hum that permeates all of space-time. The sources of gravitational waves are the most extreme, dense, and violent objects in the universe. They are the remnants of dead stars, pushed to the absolute limits of physics. We now turn our attention to these cosmic cataclysms, starting with the incredible density of the neutron star. A neutron star is the collapsed core of a massive star that has died in a supernova explosion. If the core is too massive to become a white dwarf, but not massive enough to collapse into a black hole, it is crushed by gravity to an unimaginable density. A neutron star is essentially a single, gigantic atomic nucleus, held together by gravity. The process of its formation is a spectacular event, where the core collapses in milliseconds, releasing a torrent of neutrinos that carry away 99% of the star's energy. A powerful reminder of the ghost particle's role in cosmic violence. The supernova explosion itself is a complex, multifaceted event, but the core collapse is the engine that drives the entire process, a process that is still being modeled and refined by supercomputers. The statistics are mind-boggling. A typical neutron star is only about 20 kilometers, 12 miles, in diameter, roughly the size of a city like Manhattan. Yet, it contains more mass than our entire sun. A single teaspoon of neutron star material would weigh about 6 billion tons, or roughly the weight of all the cars in the world. The gravitational field is so intense that a marshmallow dropped from a height of 1 meter would hit the surface with the energy of 1,000 tons of TNT. The escape velocity is about half the speed of light, meaning that anything that falls onto the surface hits with an incredible amount of energy, a testament to the extreme nature of the object. The interior of a neutron star is a laboratory for extreme physics, a place where matter is compressed to densities that cannot be replicated anywhere on Earth. The pressure is so immense that it forces protons and electrons to merge, creating a sea of neutrons. But the core is theorized to contain even more exotic states of matter, including quark-gluon plasma and the bizarre, hypothetical substance known as nuclear pasta. Nuclear pasta is a theoretical phase of degenerate matter that exists in the crust of a neutron star, just above the pure neutron core. As the density increases, the immense pressure forces the nuclear matter to arrange itself into complex, non-spherical shapes to minimize energy. These shapes resemble different types of pasta: gnocchi, spheres of nuclear matter; spaghetti, long tubes; and lasagna, flat sheets. This nuclear pasta is theorized to be the strongest material in the universe, a super dense, super stiff lattice that gives the neutron star its incredible rigidity. The sheer complexity of this matter, where the strong nuclear force and gravity are locked in a bizarre, high-pressure dance, is a testament to the strange and wonderful physics that lurks in the invisible remnants of dead stars. The existence of nuclear pasta is a direct consequence of the competition between the repulsive, strong nuclear force and the crushing force of gravity, a delicate balance that determines the ultimate fate of the star. The study of nuclear pasta is a key to understanding the equation of state of nuclear matter, a fundamental problem in nuclear physics. Neutron stars are often found in binary systems, orbiting another star, or, more importantly, another neutron star. When two neutron stars spiral toward each other, they create a cataclysmic event known as a kilonova. A kilonova is a merger of two compact objects, either two neutron stars or a neutron star and a black hole, that results in an explosion 1,000 times brighter than a standard nova. The final moments of the merger are a spectacular gravitational wave event, followed by a brilliant flash of light. The gravitational wave signal, the chirp, provides a precise measure of the star's masses and spins, while the light provides a wealth of information about the material ejected during the merger. The first observation of a kilonova, GW170817, was a watershed moment for multi-messenger astronomy. It was detected by LIGO/Virgo as a gravitational wave signal, and then, 1.7 seconds later, it was observed by telescopes around the world as a burst of gamma rays and a subsequent optical afterglow. This was the first time a single cosmic event was observed in both gravitational waves and light, confirming the source of the gravitational wave signal and providing a wealth of information about the physics of the merger. The observation of the electromagnetic counterpart to the gravitational wave signal was the culmination of decades of searching, a moment that truly ushered in the era of multi-messenger astronomy. The most profound discovery from the kilonova was the confirmation of the origin of the universe's heaviest elements. The extreme conditions of the merger, the rapid expansion and cooling of the neutron-rich material, provide the perfect environment for the ER process, rapid neutron capture. In this process, atomic nuclei rapidly absorb free neutrons, building up to elements heavier than iron. The kilonova explosion was observed to be a cosmic factory, synthesizing vast quantities of heavy elements, including gold, platinum, and uranium. The amount of gold created in a single kilonova event is estimated to be several times the mass of the Earth. Every piece of gold jewelry you've ever seen, every trace of platinum in your electronics, was likely forged in the violent, invisible merger of two dead stars billions of years ago. The invisible cataclysm of the kilonova is the ultimate source of the most precious elements on Earth. The study of neutron stars is not just about their density. It is about the fundamental limits of matter. The equation of state, EOS, of a neutron star, the relationship between its pressure and density, is one of the most poorly constrained areas of physics. By observing the gravitational waves from merging neutron stars, scientists can probe this EOS, effectively weighing and measuring the stars to determine how matter behaves under such extreme conditions. The chirp signal from a binary neutron star merger contains subtle information about the star's tidal deformability, which is directly related to the stiffness of the nuclear pasta in their crusts. This means that the invisible ripples in space-time are giving us a direct measurement of the properties of the hardest material in the universe, a feat of cosmic detective work that links the largest structures in the universe to the smallest, most fundamental properties of matter. The neutron star, a tiny city-sized remnant, is the ultimate laboratory for nuclear physics, and its death throes are the ultimate cosmic forge. The sheer rotational speed of some pulsars, which are rapidly spinning neutron stars, is another testament to their extreme nature. Some pulsars spin hundreds of times per second, a rotation rate that would tear apart any less dense object. This incredible stability and precision in their rotation is what makes them the perfect cosmic clocks for the pulsar timing array. A beautiful example of how the most extreme objects in the universe can be used as tools for the most subtle measurements. The study of these cosmic cataclysms is a direct link between the invisible gravitational waves and the visible light and matter that make up our world. A powerful demonstration of the interconnectedness of the cosmos. The neutron star is a silent, invisible powerhouse, a cosmic lighthouse that guides our understanding of the most extreme states of matter. From the dense, exotic matter of the neutron star, we move to the ultimate expression of gravity, the black hole. A black hole is not a star. It is a region of space-time where gravity is so intense that nothing, not even light, can escape. It is the ultimate invisible object, defined only by its gravitational influence on the visible world. The formation of a black hole is the final act of a star that is too massive to become a neutron star. When its core collapses, gravity overwhelms all other forces, crushing the matter to a point of infinite density known as the singularity. The singularity is the heart of the black hole, a point where the laws of physics as we know them cease to apply, a true edge of reality. The concept of the singularity is a profound challenge to our understanding of matter and energy, a point where all the known forces of nature are compressed into an infinitely small volume. The boundary around the singularity, the point of no return, is the event horizon. This is the invisible surface that defines the black hole. Cross the event horizon, and you are irrevocably committed to falling toward the singularity. The escape velocity at the event horizon is the speed of light. Since nothing can travel faster than light, nothing can escape. The event horizon is not a physical wall. It is a boundary in space-time, a consequence of the extreme curvature of gravity. The size of the event horizon is directly proportional to the mass of the black hole, a simple yet profound relationship that links the invisible boundary to the black hole's fundamental property. The event horizon is the ultimate cosmic one-way street, a boundary that separates the observable universe from the unknown interior of the black hole. The black hole is a source of some of the most profound paradoxes in physics, challenging the very foundations of quantum mechanics and general relativity. The first is the singularity. The singularity is a point where the density is infinite and the volume is zero. At this point, the equations of general relativity break down. The singularity is a mathematical warning sign, telling us that our current understanding of physics is incomplete. Roger Penrose's singularity theorem proved that, once a black hole forms, a singularity is inevitable, a chilling confirmation that the laws of physics as we know them cease to apply at the heart of these objects. The search for a theory of quantum gravity is the attempt to resolve this breakdown, to find a set of laws that can describe the physics of the singularity. The singularity represents the ultimate failure of classical physics, a point where the smooth, continuous nature of space-time is replaced by an infinite, unphysical density. The quest for quantum gravity is the quest to understand the ultimate nature of reality, a quest that is inextricably linked to the physics of the black hole. The second, and perhaps most famous, is the black hole information paradox. In quantum mechanics, information, the precise quantum state of every particle, can never be truly destroyed. It must be conserved. However, In the 1970s, Stephen Hawking showed that black holes are not entirely black. Due to quantum effects near the event horizon, they slowly emit thermal radiation, now known as Hawking radiation, and eventually evaporate entirely. The paradox is this: if a black hole forms from a star and then evaporates, what happens to the information that fell into it? If the information is destroyed, quantum mechanics is wrong. If the information is somehow preserved, it must escape the black hole, which violates the principle that nothing can escape the event horizon. The information paradox is a direct conflict between the two pillars of modern physics, quantum mechanics and general relativity. The resolution of this paradox is one of the most active and contentious areas of theoretical physics, with concepts like firewalls and fuzzballs being proposed as radical solutions that fundamentally alter our understanding of the event horizon. The black hole, the ultimate invisible void, is the battleground where the future of physics is being decided. The information paradox is a profound philosophical challenge, forcing us to reconsider the nature of reality and the conservation laws that underpin our understanding of the universe. The idea that information might be encoded on the two-dimensional surface of the event horizon, a concept known as the holographic principle, is one of the most radical and promising avenues for resolving the paradox, suggesting that the three-dimensional reality we perceive is merely a projection of a two-dimensional boundary. Black holes are not just cosmic vacuum cleaners, they are crucial to the structure of the universe. Almost every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. These giants, millions to billions of times the mass of the Sun, are intimately linked to the growth of their host galaxies. The relationship between the mass of the central black hole and the velocity dispersion of the stars in the galaxy's bulge is a tight correlation, suggesting that the black hole and the galaxy co-evolved. The energy released by the black hole, often in the form of powerful jets and winds, can regulate star formation in the galaxy, preventing it from growing too large. The black hole, the ultimate invisible entity, is the ultimate cosmic architect. The recent triumph of the Event Horizon Telescope, EHT, which produced the first direct image of a black hole's shadow, first EM 87 star and then Sagittarius A star, is a monumental achievement in the study of the invisible. The image is not of the black hole itself, but of the superheated plasma orbiting the event horizon, bent and distorted by the black hole's extreme gravity. The dark central region is the shadow, a region larger than the event horizon itself, where light is captured or bent away from the observer. This image is a direct confirmation of Einstein's general relativity in the strongest gravitational field in the universe, a visual testament to the invisible boundary of the event horizon. The black hole, once a purely theoretical concept, is now a directly observed reality, a silent, powerful void that shapes the destiny of a galaxies. The philosophical weight of this image is immense. We have finally seen the unseeable, the ultimate edge of reality, where the known laws of physics begin to unravel. The concept of spaghettification, the extreme tidal forces near a black hole that would stretch any object into a long, thin strand, is a vivid, terrifying illustration of the power of gravity at its most extreme. The black hole is the ultimate cosmic recycler, taking in matter and energy and returning only the subtle thermal glow of Hawking radiation, a process that will take longer than the current age of the universe to complete. The discovery of intermediate mass black holes, a missing link between stellar mass and supermassive black holes, is another active area of research, suggesting that black holes may grow through a variety of mechanisms, including the merger of smaller black holes, a process we can now directly observe through gravitational waves. The black hole is the ultimate invisible object, a cosmic paradox that forces us to confront the limits of our knowledge. We have journeyed from the ephemeral neutrino to the ultimate gravitational prison of the black hole. We've seen that the invisible particles and forces are not just peripheral oddities, they are the fundamental drivers of the cosmos. But we have saved the greatest mystery for last. The two components that make up 95% of the universe's total energy and matter, dark matter and dark energy. If the neutrino is a ghost particle, then dark matter is the ghost scaffolding of the universe, and dark energy is the ghost engine that is tearing it apart. The evidence for dark matter is overwhelming, yet we have never directly detected a single particle of it. The concept arose from the observation that galaxies and galaxy clusters were spinning too fast. In the 1930s, astronomer Fritz Zwicky observed the Coma cluster and found that the galaxies within it were moving so quickly that the cluster should have flown apart long ago, based on the visible mass. He concluded that there must be a massive unseen component providing the extra gravitational glue. Zwicky's initial observation, based on the virial theorem, was largely ignored for decades, a testament to the human tendency to dismiss evidence that contradicts established paradigms. The most compelling evidence comes from the galactic rotation curves. Stars in the outer regions of a spiral galaxy orbit at the same speed as stars closer to the center. According to Newtonian physics, the orbital speed should decrease with distance from the center, just as the outer planets in our solar system orbit slower than the inner ones. The only way to explain the flat rotation curve is if the galaxy is embedded in a massive spherical halo of invisible matter that extends far beyond the visible disk. This is the dark matter halo. The shape and extent of this halo are crucial to the stability and evolution of the galaxy. A silent, invisible guardian that holds the visible stars in their orbits. The rotation curve is a direct, undeniable signature of the presence of a massive, invisible component that dominates the galaxy's mass budget. Further confirmation came from the Bullet Cluster, a system of two colliding galaxy clusters. Observations showed that the visible matter, the hot gas detected by X-rays, was slowed down by the collision, but the gravitational lensing, the bending of light from background galaxies, showed that the majority of the mass, the dark matter, passed right through the collision without interacting. This was the first direct, visual separation of dark matter from ordinary matter, a smoking gun for its existence. The Bullet Cluster provided irrefutable evidence that the gravitational mass of the cluster is spatially separated from the baryonic mass, a powerful confirmation that dark matter is a real, physical substance. The gravitational lensing effect is a direct measure of the total mass distribution, and the fact that the mass peak is offset from the X-ray peak is the clearest evidence yet for the existence of a non-interacting form of matter. Dark matter is a particle that interacts only through gravity and perhaps the weak nuclear force. It does not emit, absorb, or reflect light. It is the invisible scaffolding that allowed the cosmic web to form, providing the gravitational potential wells for ordinary matter to fall into. The search for the WIMP, weakly interacting massive particle, or the axion, is one of the most intense experimental efforts in physics, involving massive underground detectors like the Lux-Zeppelin LZ experiment, shielded from all other forms of radiation, waiting for the faint, rare interaction of a dark matter particle. The philosophical implications of dark matter are profound. It means that the universe we see is merely a luminous afterthought, a 5% veneer stretched over a 27% invisible gravitational skeleton. The visible universe is the exception, not the rule. Our entire existence is predicated on the existence of this unseen mass, which provided the necessary gravitational seeds for the formation of the first stars and galaxies. Without dark matter, the universe would be a uniform, featureless soup of gas, and we would not be here. The search for the nature of dark matter is not just a search for a particle, it is a search for the true nature of the universe's foundation. The possibility that dark matter is composed of sterile neutrinos, a hypothetical, much heavier cousin of the ghost particle we started with, provides a tantalizing link between the smallest invisible particles and the largest structures in the cosmos. The alternative theories, such as MOND, modified Newtonian dynamics, which suggests that gravity itself behaves differently on galactic scales, are a constant reminder that our understanding of gravity may be incomplete, and that the invisible mystery may be a flaw in our own equations rather than a new particle. The hunt for dark matter is a global effort, a race to discover the particle that holds the universe together, a particle that is all around us, yet utterly invisible. Finally, we confront dark energy, the ultimate invisible force. In 1998, two independent teams of astronomers studying distant Type I as supernovae, standard candles used to measure cosmic distances, made a shocking discovery. The expansion of the universe is not slowing down due to gravity, as everyone expected. It is accelerating. This acceleration requires a source of repulsive gravity, a force that is pushing space apart. This force is dark energy, and it makes up 68% of the total energy density of the universe. Unlike dark matter, which clumps together, dark energy is thought to be a property of space itself, a constant energy density that permeates all of space. It is the cosmological constant, a concept Einstein once called his greatest blunder, now resurrected as the dominant force in the cosmos. The discovery of dark energy was a profound shock to the scientific community, a complete reversal of the prevailing cosmological paradigm, and it earned the discoverers the Nobel Prize in 2011. Dark energy is the ultimate invisible engine. It is the reason the universe will end in the Big Freeze, tearing apart the cosmic web and isolating our future island galaxy. Its nature is the most profound mystery in physics, challenging our understanding of the vacuum of space itself. The simplest explanation is that it is the vacuum energy of space, but quantum field theory predicts a vacuum energy density that is 10 to the power of 120 times larger than what we observe. A discrepancy known as the cosmological constant problem. This is the largest disagreement between theory and observation in the history of science, a profound crisis that suggests a fundamental misunderstanding of the relationship between gravity and quantum mechanics. The fate of the universe hinges on the precise nature of dark energy. If it is a true cosmological constant, the expansion will continue indefinitely, leading to the Big Freeze. If it is a dynamic field, known as quintessence, its properties could change over time, leading to a different, perhaps more dramatic, end to the cosmos. The study of dark energy is a quest to understand the ultimate fate of the universe, a quest that is inextricably linked to the nature of the vacuum itself. We began this journey with the question, what is reality made of? The answer is a humbling one. The visible, tangible world, the stars, the planets, the life, is a mere 5%. The rest is a hidden, invisible architecture of particles and forces that we are only just beginning to map. The mystery of the invisible space particles is not a tale of failure, but a testament to the power of the human mind. We cannot see them, but we can infer their existence through the subtle, profound effects they have on the visible world. We have used the laws of physics to see beyond the limits of our senses, to map the ghost scaffolding of the cosmos, and to listen to the silent gravitational roar of merging black holes. The universe is a book written in a language we are still learning, and the invisible particles are the most complex, beautiful characters in that script. Our journey is a celebration of the ongoing hunt, the relentless pursuit of the hidden truth that makes up the vast majority of our reality. The hunt continues and the invisible awaits. Before we conclude, let us pause to consider the profound philosophical implications of this invisible universe. The fact that 95% of reality is hidden from us is not a limitation of the universe, but a limitation of our current perception. It forces us to redefine what we mean by seeing. We have moved from a universe where seeing was believing to a universe where believing is seeing, where the most profound truths are revealed not by the light of a telescope, but by the mathematics of a theory and the ingenuity of a detector buried deep underground. The invisible components of the cosmos, the neutrinos, the gravitational waves, the dark matter, and the dark energy, are a constant, humbling reminder of the vastness of our ignorance. They are the cosmic unknown unknowns. Every discovery we make, from the oscillation of the neutrino to the acceleration driven by dark energy, does not simplify the universe. It reveals a deeper layer of complexity. The universe is not a simple machine waiting to be fully understood. It is an infinite onion, and every layer we peel back reveals a new, more mysterious layer beneath. Consider the anthropic principle in the context of dark energy. The value of the cosmological constant as incredibly small, almost zero. Yet it is large enough to accelerate the expansion of the universe. If it were slightly larger, the universe would have expanded too quickly for galaxies to form. If it were slightly smaller, the universe would have collapsed back on itself. The fact that the value is precisely tuned to allow for the formation of stars, galaxies, and life is a profound coincidence. Is this a mere accident, or does it suggest a deeper reality? Perhaps a multiverse where every possible value of the cosmological constant exists, and we simply find ourselves in the one that allows for our existence. The invisible force of dark energy, the ultimate engine of cosmic expansion, forces us to confront the possibility that our universe is just one bubble in an infinite, unseen sea of realities. The hunt for the invisible is, in essence, the hunt for the fundamental nature of reality. It is a quest that transcends physics and enters the realm of philosophy. The invisible particles are the cosmic whisper that reminds us that the greatest adventures are not found in the light but in the dark, where the true, profound mysteries of existence reside. The journey into the invisible is the ultimate human endeavor, a testament to our insatiable curiosity and our relentless pursuit of the truth, no matter how elusive it may be. The invisible is not empty. It is full of the most fundamental, powerful, and mysterious components of the cosmos. And as we continue to build our deep detectors and listen to the silent whispers of the universe, we are slowly, painstakingly bringing the invisible into the light. The final frontier is not space, it is the unseen. The mystery of the invisible space particles is not a tale of failure, but a testament to the power of the human mind. We cannot see them, but we can infer their existence through the subtle, profound effects they have on the visible world. We have used the laws of physics to see beyond the limits of our senses, to map the ghost scaffolding of the cosmos, and to listen to the silent, gravitational roar of merging black holes. The universe is a book written in a language we are still learning, and the invisible particles are the most complex, beautiful characters in that script. Our journey is a celebration of the ongoing hunt, the relentless pursuit of the hidden truth that makes up the vast majority of our reality. The hunt continues, and the invisible awaits. The story of the invisible space particles is a story of scientific humility and triumph. It is a story that began with a crisis, the missing energy in beta decay, and has led us to the brink of a revolution in physics. The journey from Pauli's desperate remedy to the direct detection of gravitational waves is a narrative arc that spans a century of human ingenuity. It is a reminder that the most significant breakthroughs often come from looking not at what is there, but at what is missing. The next chapter in this story is being written right now. The search for the dark matter particle is intensifying, with experiments moving from the search for WIMPs to the more exotic, lower mass candidates like the Axion. The Axion Dark Matter Experiment, ADMX for instance, is using a massive superconducting magnet and a microwave cavity to try and convert axions into detectable photons, a delicate search for the faintest whisper of the universe's missing mass. The sheer scale of these experiments, requiring international collaboration and billions of dollars of investment, underscores the importance of this invisible component to our understanding of the cosmos. Simultaneously, the quest to understand dark energy is driving the next generation of cosmological surveys. Projects like the Dark Energy Spectroscopic Instrument, DESI, and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are mapping billions of galaxies to precisely measure the expansion history of the universe. By charting the distribution of galaxies over cosmic time, these projects aim to determine if dark energy is truly a constant or if it is a dynamic, evolving field. The answer to this question will not only determine the ultimate fate of the universe, but will also provide the crucial clues needed to reconcile quantum mechanics and general relativity. The invisible particles are not just abstract concepts. They are the key to a unified theory of everything. The standard model of particle physics, for all its success, is fundamentally incomplete because it cannot account for gravity, dark matter, or dark energy. The existence of these invisible components is a signpost pointing us toward a deeper, more comprehensive theory, Perhaps supersymmetry, which predicts a partner particle for every known particle, or string theory, which posits that all particles are tiny, vibrating strings. The invisible is the engine of the next great scientific revolution. Let us take one final moment to reflect on the profound shift in perspective that the invisible universe demands. For millennia, humanity believed that what we could see was all there was. The stars were pinpricks of light, the planets were wandering gods, and the earth was the center of a knowable, visible cosmos. The invisible components of the universe have shattered this anthropocentric view, replacing it with a cosmic humility. We are not the main characters in this story. We are the fleeting observers of a reality that is mostly hidden. The search for the invisible is a testament to the power of indirect evidence. We have never seen a neutrino, yet we know its mass is non-zero. We have never seen a dark matter particle, yet we have mapped its gravitational influence across the entire cosmic web. We have never seen dark energy, yet we know it is the dominant force in the universe. This reliance on inference, on the subtle effects of the unseen on the scene, is the highest form of scientific reasoning. It is the ultimate cosmic detective work, where the clues are not left at a crime scene, but are woven into the very fabric of space-time. The invisible is the ultimate challenge to our intuition. Our brains evolved to navigate a world dominated by electromagnetic forces and baryonic matter. The concepts of quantum oscillation, space-time curvature, and repulsive gravity are not intuitive. They are hard-won intellectual victories. The invisible universe is a constant reminder that reality is not obligated to conform to our expectations. It is a canvas of profound, counterintuitive truths, and the invisible particles are the brushstrokes of the cosmos. The ultimate reward of this journey is not just scientific knowledge, but a deeper sense of wonder. To know that you are constantly being bombarded by trillions of ghost particles. To know that the chair you are sitting on is held together by a force that is merely a ripple in a four-dimensional fabric. To know that your galaxy is an island in a sea of invisible mass. This knowledge transforms the mundane into the miraculous. The invisible is the source of the sublime, the profound realization that the universe is far grander, far more mysterious, and far more alive than we could have ever imagined. The invisible is the future of physics. It is the unknown that drives the known. And as we continue to listen to the whispers of the cosmos, we are not just discovering new particles, we are discovering a new definition of reality itself. The invisible is waiting. Let us continue the hunt. Thank you for joining us on this deep dive into the unseen. If you are captivated by the mystery of the invisible, please let us know by hitting the like button and subscribe to Cosmo Depth for more journeys into the profound and the unknown. Until next time, keep looking up and keep questioning the nature of reality.